So what we want to show is, to do our proof of our formula, we're going to begin with the formula phi n overlapped with psi. And what we really hope to get, right, I'm not making a circular argument, I'm not claiming this is equal, I'm just trying to keep in mind where I'm trying to get. I'm hoping this will just give me the nth coefficient of the energy representation. Now, what I can say for sure, without making any assumptions, is that this overlap I can actually relate to these coefficients using the very superposition whose coefficients I'm trying to determine. In other words, I am guaranteed by quantum principle of superposition that for psi here, I can actually insert its expansion. And the expansion is sum on n times the weights Wn times my pure states phi sub n. Now, the next thing we should do, and that I want to be very careful about, is you will notice I've just done something where I've taken a somewhat complicated expression. It looks simple, but this notation represents some complicated integral. And what I've done is I've substituted into it a sum. And hopefully by now in the course you've been well trained that whenever I insert a sum or an integral into a more complex expression, I need to be very careful about the dummy integration variable, or in this case, the dummy summation variable. This n in here that varies over all possible indices, right, that make up my sum. They count over all the possible states of my system. But what happens is I use them to form this sum, and then once this sum is done, right, I've sort of used up that dummy summation variable. It's, again, somewhat like calling a function subroutine in some kind of a computer code, right? This n is just the temporary variable I use to compute the sum just before I return the value of the sum into the rest of my expression. So this n, notice, has a very different meaning from the n that I have here on the left side. The n over here on the left side has a particular value. Its value is the function whose overlap I'm computing, and ultimately that n is the coefficient that I'm trying to compute. So this n and this summation m have different names, and we don't want to confuse them in our derivation. So what we would do is simply change, if you will, the name of this temporary variable inside my computer function, or just simply to relabel the dummy summation index. So let's call this m inside my sum. That doesn't change the value of my expression, but now it prevents me from making silly mistakes as I manipulate this integral further. Next, let's take a look at this. Now, you all have proved on various assignments a set of nice algebraic rules for how to manipulate expressions involving these types of inner products. And I want us to get used to just manipulating them in this much more compact notation. It kind of helps to much better organize our thinking. So this is maybe the second to the last time I'm going to write down the traditional integral representation just as a crutch to help us with this particular derivation. So this is also equal to, remember the definition of the Hermitian inner product, it would be the integral, right, of the star of what's on the bra side, on the ket side, with then the function that makes up the bra part. So this is the Wm phi sub m of x. Now, let's try to manipulate this integral. I don't want to think about it as an integral, though. I want to focus on Hermitian inner product. This is just to help inspire us. So you may recall that one of the nice properties of a Hermitian inner product is that it is what is known as a bilinear function. It is linear in both the bra part and in the ket part. So what that means then is if I have a bra ket that has a sum, it's equal to the sum of the bra kets. Just like the integral of a sum, we know, is the sum of the integrals. So I can pull the summation part out. So I can rewrite this as sum on m. Then I would have just phi n inner product with Wm phi sub m, which is just like where I would have pulled out this summation. Now I have this Hermitian inner product, but again, it's a bilinear form. That means if I have a constant, I can pull it out of the bracket. Just like after I've pulled out this sum, this w, you will notice, is just a constant. I can always pull a constant out of the integral. So the next step in my analysis would be sum on m. I have the wm, and then I have the overlap between phi n and phi m. Now, the next time we come across something like this, by the way, I hope we will be able to quickly recognize and we can pull both the sum and the coefficients out. Now, looking at this, I'm very excited, actually, because this is a quantity that I know very well. This is the overlap of two of my pure energy states. This is the Kronecker delta function. So I know I will be able to replace this with my Kronecker delta. And now I'm going to learn something new, right? I now have a sum over an expression with a Kronecker delta. This is very much like the same logic we used when we had an integral over a function that involved a Dirac delta function. It's going to be very similar logic. And the logic for this goes as follows. When I think about this sum, notice I will have a large number of terms, one for every value of m, but almost all of these terms are going to be 0, right? Only one of these terms will not be 0 when m equals n. So let's break up this sum into those two classes of terms. So one class of term has m, which isn't equal to the value n, and there's a whole series of those terms, but they all are giving me zeros. So I get 0 for all of those terms. And then the alternative is there's just one other type of term when m equals n. So I can write down my summand for the case m equals n. Well, if m equals n, then I have w sub n for that term. And then the rest I have is my Kronecker delta, delta n n. And of course, delta n n has the value 1. And I have just 0 plus 1 times wn. Well, that's pretty easy. That just pulls out wn. And this is something I'm very excited about, right? This is great because that is exactly what I was hoping to prove. So now we know precisely how to extract these weights given a wave function. And then once we have those weights, we also know how to calculate the probabilities. So that is that final result proved for us. Maybe I'll put a box around this, phi n with psi. Now, we should be a little careful because this overlap actually is not wn factorial, right? So maybe that's a bad notation. Instead here, maybe we will draw a nice smiley face, and maybe I'll have it look at a professor because the professor is very happy here after seeing that we can basically have the right analog for the Fourier inversion theorem. So that's my symbol. That something worked out very nicely for us. Okay, so we can put a box around this one. Very handy expression.